and welcome to the lecture number 4 of Physics 401A. In this lecture, we will mainly discuss some terminologies. Before starting the so-called Lagrangian formulation of classical mechanics, which is the first principal objective of this course, we will start by getting ourselves familiar to the very vocabulary of generalized variables. You will come across this word generalized a million times in this course. So maybe this is the occasion to give you a formal introduction to all these generalized variables. So as I mentioned in the very beginning of this discussion that unlike Newtonian mechanics, Lagrangian and Hamiltonian mechanics or formulation, they employ generalized coordinates and actually generalized variables. Okay. Now, what is a generalized coordinate? You know that basically in case of normal mechanics, whenever we talk about coordinates, that is to locate a particle or locate an entity. Okay. In space, that is the coordinate, right? And also that can be, we can also say in space-time, if we try to locate some event or something, then space coordinate and time coordinate, they are necessary, right? So, you know that the number of coordinates, basically the number of necessary coordinates, basically, they are exactly equal to the dimension of the space where the particle or the entity is situating. Okay. Now, of course, you know that these quantities, these coordinates can have interrelations according to the constraint of the problem. For example, let's say a sphere in 3 dimension, we all know that, so any point on the sphere needs 3 coordinates, rather r, theta, phi, to get identified or to get, to get identified or to get located. Now, if I just say that I make the surface of the sphere fixed, that means I am fixing the radius of the sphere. Okay, the sphere cannot inflate or cannot contract radially. Then, of course, we need only 2 coordinates there, theta and phi. Right? So this type of thing is just saying that whenever we have some constraint, then basically according to the constraint, the number of degrees of freedom may reduce. Okay. So in generalized coordinate, basically we already take into account all the effects of these constraints. Now whenever I say that, it is very good to say that it will be mostly noticeable or mostly direct, this number of reduction of coordinates according to the constraint, only when we have very well behaved algebraic constraints. Sometimes non-algebraic constraints can also be handled in algebraic way. That is I will discuss further in some discussion session. This type of algebraic constraints are called holonomic constraints. Okay. So mostly whenever we talk in this context, for simplicity, the constraints we mean holonomic constraints. So whenever I say that a particle should be located on a surface of surface of sphere with fixed radius, then we know that for that one, x square plus y square plus z square is equal to a constant, right? Or we can say, the root over of this is a constant, or the square is also a constant, you all know. Or the r, theta, phi now have its r to be constant, right? So whenever you say that something is equal to constant or something is related to something by some algebraic equation, then basically you have a holonomic constant. If you have an inequality or something, maybe I will give you a small overview of constraints in some discussion session. That can be done. Okay. Now, whenever we are talking about this generalized coordinates, basically The generalized coordinates are the minimal number of independent variables which can describe the configuration of the system complying with all the constraints of motion imposed. So that means whenever I say that what is the set of the generalized coordinates needed to describe the motion of a particle on a sphere surface with fixed radius r, then the answer will directly be theta and phi. Whereas if I say what are the number of coordinates necessary, then I can say the coordinates necessary are r, theta, phi given or under the constraint r is equal to constant, right? That is, I mean, that's another way of saying, okay. Now, why we call, so basically I have to underline this word here, so at the minimal number of independent variables. So the number of generalized coordinates must be a subset of the normal coordinates, okay. And these generalized coordinates, they also must be mutually independent of each other. That is very crucial, okay. And they are complying with all the constraints of the motion, okay. Here we are talking about only holonomic constant for simplicity. Now, why are they called generalized? Because in general, as we will see, as the course will go on, we will see that they can be anything like distance, or in general we know that the space coordinates, they are given by the distances, right? Or sometimes it can be angles. But whenever we write the vectors or the vector form, the position vector form or something, so everything should be of the same type of unit. Let's say whenever we say that the coordinates are given by x, y, z, then all of them are having that distance, I mean unit of distance. Whereas whenever we are talking about r, theta, phi, we don't say that r, theta, phi, all of them are of the same footing, right? And so two of them are angles and one is r. That's why when we are talking about only the position vector, it's only r which is coming into play. That's why we just say that r vector is nothing but scalar r times r unit vector, right? Theta and phi don't come into play in that, right? That we have to understand. In case of these generalized coordinates, this is also the same thing. So generalized coordinate, in any case, we will try to make our formulations in such a way that we will put all the coordinates, whether they are distances or angles or amplitudes in a Fourier series or distance along a curve, okay, that means curvilinear distances, or even some other things like energy, angular momentum, okay, in an equal footing. Why this is so, you will understand why when I will really derive the equation of Lagrange. I mean Lagrange or Euler-Lagrange equation of motion. Then you will understand why I am talking of this. So whether this is distance or this is an angle, all of them are put in an equal footing with respect to the governing equations of this formulation. And what is this governing equation? This is called Euler-Lagrange equation. That I will derive in next lecture, probably. Okay. So another thing is that for a system, a judicial choice of generalized coordinate is thus necessary to easily obtain the equation of motion. So a judicial choice of generalized coordinate is necessary because one thing I have to state here, that the choice of generalized coordinates is not unique. So you can choose a separate, I mean one set, and I can choose another one, and maybe one can be more handy than the other, that's all. But one is wrong, one is right, that is, I mean, of course that is possible that I have chosen a wrong set. That's possible because maybe they are not independent, maybe they are not complying with the constraints, maybe they are not giving the minimal set of coordinates. But even if both of them are correct, one can be less or more useful than the other. That's also possible. Okay. So, how to really choose a good set or a useful set of generalized coordinate? We have to pick the right symmetry. For example, when we are talking about, for example, the motion of conical pendulum, the first thing, conical pendulum in 3D space, of course, the first thing which comes to our mind is the cylindrical symmetry. But when we are talking about linear, normal simple pendulum, we just can think of one-dimensional problem, which is simply a problem of, a reduced problem of 2D plane polar coordinates with r constant that we will see in a second. So those two symmetries are of the same type, maybe here, but one is cylindrical symmetry, another is a planar symmetry. Okay. Again, when we are talking about, let's say, spherical pendulum, that I will talk just after, maybe after this lecture. Okay, you will see that then again proper spherical symmetry will be interesting, right? So try to understand how to really think of choosing these generalized coordinates. So let's say the case of simple pendulum moving in a vertical plane. As you can see that this is the plane of the paper where this is moving, and the length of this pendulum is fixed. That is the constraint. So it makes the r fixed. So although we know that the problem is of plane polar symmetry character, so it should have two coordinates, r and theta. Now according to the constraint, r is fixed, so we only have one generalized coordinate, theta, right? So if we have only one generalized coordinate, theta, then basically theta is something which is the only coordinate, because it is only one, so we don't have to check whether this is mutually independent with the others or not. That is the trivial, the simplest case. But only one thing we can say, that this is complying with the constraint that r is equal to constant. So only theta can vary, and that is completely understandable over here, right? Now, why we are talking about this plane polar symmetry? Because we said that we have to pick the right symmetry. That is our responsibility to here talk, or rather to justify why we have chosen this plane polar symmetry, right? That is simple, because this pendulum's motion is nothing but sweeping out a part of the perimeter of a circle, and for a fixed length, this is the perimeter of a circle of fixed radius. Because as you can easily understand, this if you just follow the cursor over here, this will give you a circle, right? So that's why this is a plane polar symmetry type of problem. Okay. Now if we are talking about the motion of a rigid body in 3D space, then we know that basically at the base we need 6 generalized coordinates, because the degrees of freedom of a rigid body in general, when the rigid body is, how to say, is a continuously constituted body, you can say that it has 3 translational degrees of freedom. That means the coordinates of its center of mass, for example, and 3 angles which are describing its rotational degrees of freedom. Generalized rotation in 3D space can be described by 3 characteristic angles. One of the possibilities is, that can be many type of angles. One is Euler angles, another is Bryant-Rate angle. You all know maybe. Okay, so 3 degrees of freedom for translation, 3 for rotation. So we need, the system has 6 degrees of freedom as a whole. So we need 6 generalized coordinates. Now, which 6 generalized coordinates to be chosen? Of course, you can now understand also that will be simply the normal coordinates of the CM and 3 Euler angles, for example. One possibility. Okay. Now, let me ask you one question. What will be the set of generalized coordinate for a ball rolling down an inclined plane? Okay, the ball is not spinning in other ways or something. So for example, if you you can confuse between a ball or a cylinder. Here this is the same. I can also talk about a cylinder. So a cylinder is just rolling down without slipping. That means the friction is enough to prevent the slipping of this cylinder or the ball, okay, through the inclined plane. And the inclined plane has a constant inclination theta. So think, and maybe you answer me in the discussion session or in the discussion forum. Okay. Now let me introduce the symbols which we traditionally use for this type of generalized coordinates. They are denoted by QIs. Okay. Now here you can easily see I can range from 1 to small n, where small n is the number of degrees of freedom of the system. Now, as I just said some minutes ago, that the choice of generalized coordinates are not unique. So between two sets of generalized coordinates which are correctly chosen, one can be both of which are correctly chosen, one can be less or more handy than the other depending on the problem, or rather the symmetry of the problem. Okay. I told you to check more about holonomic constant, that you can also do. Okay. After defining these generalized coordinates, we introduce generalized velocity as qj dot ddt of qg. These things are known as generalized velocities. Now try to understand one thing. In this case, we are just always talking about this variables, okay, a set of such variables which are of non-uniform, may or may not be of non-uniform units. One can be angle, one can be distance. So this is a set of such things. So we in this generalized formulation, we don't want to make a generalized position vector. This is not possible. Think about this. And the same thing for this, as qj can be an angle, qj can be a distance, then ddt of qj can be angular velocity, for example, right? As I said, if qj is an angle, then qj dot is an angular velocity component. If qj is position coordinate, then qj dot is linear velocity coordinate. So we will not try to make a generalized velocity vector, for example, right? Q dot bar or q dot vector. That doesn't have any meaning in this case. Okay. Now for a system, okay, let me just somehow underline this point, that if qj is a position coordinate, if qj dot will be the normal velocity and qj is an angle, then qj dot will be angular velocity. Okay. Now for a system, all these qj's, qj dots and time, they are mutually independent by construction. That you have to understand. Now here many questions may come, I know, that's why I try to here clarify a bit. Although one should remember that in reality both qj and qj dot, they are functions of time, okay. But when we use qj, qj dot and even t to describe the state of classical mechanics, the state functional, okay, which we will learn in some, maybe in the next lecture, that is Lagrangian, for example. Okay, the state functional can be written in terms of qj, qj dot and t, and of which one of them can always be varied without disturbing the other. That is important, and that's why when we are talking about that functional or the description of a classical mechanical state, then we talk about the mutual independence of qj, qj dot and t. So once again, another way of saying that actually the state functional may depend explicitly on t, or whenever it depends on qj and qj dot, basically it has an implicit dependence on t through qj and qj dot. Okay, think about this, okay, and then if you have again doubts and confusions, ask me, no problem. Okay. Let me, maybe for clarification, let me just give you one example. What can be this thing? So let's say that you have a potential. You all know about potential, right? So the potential in general we know, unless there is some dissipation type of mechanism or anything, very special potential. We will do some of them actually, maybe one of them at least. In general, the potentials are of, they are purely functions of position coordinates, or rather generalized coordinates, right? In Newtonian mechanics, you know, they are not functions of velocities but functions of positions. And they are also not functions of time, not explicit functions of time. Now, we all know that position changes with time, right? But the, this is, that dependence is not accounted when we talk about this dependence on of the potential on the position. Okay. Now, let's say we are talking about that whether, so now the question is whether we can alter, or we can think of varying the potential for a given time at different points or not. Yes. And if we can do that with respect to that potential function, basically, so basically this means that you are fixing an instant of time, and basically you are taking a snapshot. Then you have 2 points in space, and you calculate in 2 different points 2 different potentials. That's possible. The time is not changing, but the space points are different. Okay. So if it is possible, then when we are talking about that potential. Okay, then you can say that this is also in terms, it's type of is a functional, okay, with respect to t, because the position is a function of t, and q is, potential is a function of that position. So that functional basically can have 2 different values at 2 different positions for a given time t. Now we can make an explicit dependence on the position, on the potential, by making the potential as a periodically varying potential, which can be derived, or rather which can be, which can be obtained by using a periodic force, for example, right? Like a sinusoidal type of force. Then if you integrate, you know that of course you always have another periodic potential as well, sine cosine type of potential, right? So then it will have a explicit time dependence. Okay. So this type of thing, think over that. Okay. If you are not, if you have a doubt, do not hesitate to ask me. I will try also to clarify as much as possible. Now let us suppose that we have a system of n particles, and if they are free from any constraint, then the system would have 3n degrees of freedom. Okay, that's completely yes, no problem, because all of them are point particles, so they don't have any structure or rotational degrees of freedom or something. So 3n translational degrees of freedom, very simply speaking. If they have k holonomic constraints, that means k algebraic equations of constraints, then the system would have now small n, which is 3n minus k degrees of freedom. Then the system would require n number of generalized coordinates, small n number, and we must have these type of relations where every single normal position vectors of the capital N particles can now be written in terms of all the generalized coordinates of small n number and t eventually, if t is needed at all. Okay. Then we can write Ri dot, which is the normal velocity, as del Ri del t. Ri dot is dri dt, so now it will have these components del Ri del t plus summation over j1 to small n del Ri del qj dot, right? So we call Ri dot as Vi vectorially. Then if in these transformations we don't have any explicit time dependence, then we can easily forget this term. This term would vanish. That I have not mentioned here explicitly, sorry for that. But this term will then vanish, and we simply have Vi vector is equal to summation over j del Ri del Qj times Qj dot. Now note, when we are talking about simple Cartesian components normally, then Ri is nothing but xi, yi and zi. Then xi dot, that means the x component of the velocity for ith particle, okay, will simply be summation over j, where j varies, I mean j ranges from 1 to small n, del xi del qj times qj dot. Of course, assuming that this is concerning such a transformation to such a set of generalized coordinates where explicit time dependence is ignored. Okay. Now, if we think about the variation which we just talked in the previous lecture, or an arbitrary virtual variation of Ri, then that will simply be given as delta Ri, which is equal to summation over j del Ri del Qj times delta Qj. Now remember, this is nothing but delta Qj is nothing but the variation or the change of Qj just by changing those alpha parameters, okay, and keeping t, or if you remember for the previous example, the x, which is the intrinsic independent variable, constant. Okay. Now here you can see that the term which is del Ri del t, delta of t is missing, because delta of t is always 0 by definition, right? Okay. Now we write the acceleration. The normal acceleration is Ri double dot, and that will simply be ddt of this Ri dot. Okay. Now simply substituting this expression over here, you have three terms. ddt of this, which will give you two terms. So ddt of del Ri del Qj times Qj dot plus del Ri del Qj double dot, because ddt of Qj dot is Qj double dot, plus ddt of del Ri del t. Okay. Now again, just by expanding ddt, you can see that as all Qj dot and t, they are all mutually independent, these two operators commute each other, and so for ddt and del t. Okay. Using this, we simply can have Ri double dot is equal to summation over del Ri dot del Qj dot plus del Ri del Qj double dot, both are summed over j, plus del Ri dot del t. Again, you can substitute the values of Ri dot in this total expression, and that will simply give you this bigger expression. Okay. And we finally have 5 type of terms. One is double summations, both are on the number of degrees of freedoms, del 2 Ri del Qj del Qk, Qk dot Qj dot, or you can write Qj dot Qk dot, doesn't matter, summation over j del 2 Ri del Qy del t Qj dot, then summation over j del Ri del Qj double dot, plus del 2 Ri del Qk del t Qk dot summed over k or summed over j, whatever, the same type of thing. As you can see here, I have just deliberately chosen different type of dummy indices so that you get familiarized with this type of dummy indices. This can be anything. Okay. And finally del 2 Ri del t2. Okay. So the total acceleration can now be written in terms of the generalized coordinates and generalized velocities, actually, in this way. So that's equation 4. Okay. Now if we write the kinetic energy, then kinetic energy T is equal to, as we all know, is simply nothing but the half of mi ri dot square summed over I, and then we simply substitute the values of ri dot over here, and we have four type of terms, exactly what we have written here. And the two cross terms, that means this one times this one and this one times this one, they will be of identical nature, and that's why they will add up by giving something like this. You can check at home. Finally, you can see that the kinetic energy has three type of terms as a whole, and this one is quadratic in generalized velocities. This one is linear in generalized velocities, and this one is independent of generalized velocity. Okay. Once again, as you can easily understand, whether this is here or I don't know, maybe here as well, and here, okay, and this term as well. Okay, so whenever we have this type of transformations which are free from explicit time dependence, then we have del Ri del T is equal to 0, and we have simplification for kinetic energy. We have these two terms vanishing under those and under that assumption of time independent transformation, coordinate transformations. So we simply have this term that we can write. Now this term can involve cross terms. I mean, j and k may or may not be equal. Now if we are considering such a generalized coordinate system, which itself is another orthogonal coordinate system, then we know that this type of cross terms will not be allowed, because del Ri del Qj will give you the unit vector towards Qj, and del Ri Qk will give you another unit vector towards Qk, right? And finally, what will happen, that these two being perpendicular to each other will give you 0 under dot product, and then it is non-zero only when j is equal to k. Then the style of writing this whole expression for an orthogonal system is like this. Now remember, in general, for a generalized coordinate system, okay, this is not true. This is only true if the generalized coordinate system constitutes a normal, like it's identical to another usual orthogonal coordinate system. Okay. Now we talk about another very important concept, that concept of generalized momentum. So in normal case, if we just think that T is equal to half mi ri dot square just for ith particle, then we can of course have the sum for having the total kinetic energy, and the corresponding momentum. I have had to write actually this here Ti and Pi, so please edit that. Okay, so it will be Ti and Pi, and then clearly you can easily understand that this is nothing but this is nothing but the compact way of writing P. If we just write P is nothing but the velocity gradient of T, or rather gradient of T in velocity space. So that means you are taking the gradients but not in space but velocity, just with this expression. Okay. If you do that, you can easily understand this will simply give you Pi. Okay. Again, this is Ti. I am sorry for this. That will be Mi. Okay. Well, there are too many typos, so please check all these things. Okay. Now we can generalize this definition by defining Pk is equal to del T del Qk dot, and we call this as kth component of generalized momentum. We again say that we don't like generalized velocity, we don't try to constitute a generalized velocity vector. Rather, we try to make a set of variables, and we will say that is the that set of variables constitute the generalized velocities. That's a set of variables. This constitutes the generalized momentum, for example. So here the pk's, k varying from 1 to n, that constitutes the generalized momentum. Okay. Now we take an example how they should look like. So for a particle just performing 2D motion under a central force, the kinetic energy is half m r dot square plus r square theta dot square, and we simply identify for this very easy case q1 is equal to r, q1 dot r dot, q2 is theta and q2 dot as theta dot. So then PR will be del T del R dot, which is equal to m R dot, which is usual linear momentum component, right? And P theta is del T del theta dot, which gives us m R square theta dot. See, here this is no longer the usual momentum, this is the angular momentum component. Now you remember, you can easily understand that this PR has a direction, and this P theta has a direction. Both these directions are not really. So for example, if you just take basically the direction of PR, this is, this is r cap, right? Isn't it? This is r cap. Okay. Now what is the direction of P theta? This is not simply theta cap. This is z cap. Okay, so that's why I said that just don't constitute the vectors out of this generalized coordinates or generalized velocities or generalized momentum. Okay, they are very good, they are very well as an ensemble or a set or collection of variables. Okay. We also define two important things. One is virtual work. So virtual work is nothing but the scalar product of force with virtual displacement. Now you all know the virtual displacement, and you also know how to describe or express this in terms of the generalized coordinates. And if you write that, then you can actually take this fi dot summation over j1 to n del ri del qj separately times del qj. So it will then be written, this virtual work, as something times del qg, and this something, okay, which is so this something is a summation over jqj and can be called as summation over fj, where summation over this thing, okay, this summed over this total part can be called as summed over qj, where qj is nothing but fi dot del ri del qj. Okay, and this qj is known as generalized force. Okay, so that is just giving analogy. If you have normal coordinate, normal this position vector, then it will be your usual force vector. If we have generalized coordinate, then this will be generalized force component. Simple as that. Okay. So here I end this lecture number 4, and in the next lecture we start discussing Hamilton's principle and the formal derivation of Euler-Lagrange equation. Thank you very much.